All right, so last class we started looking at the chain rule. We started doing some of those questions. And I know I went through like a really hard one at the end, but even before that, I don't think you totally got it. So we're going to start off with the chain rule and go through it a little bit more because we're going to need it to go forward with today anyway. All right, so let's look at this one. Y equals e to the sine of x. So what's the derivative of e to the x? Right, it stays the same, right? So we might think that the integral or the derivative of e to the sine of x is just e to the sine of x. However, because there's something up here, because there's that piece up in there, it doesn't work that way. That's where that chain rule comes into play. Okay. So what is the derivative of sine of x? That goes to cosine of x, right? That's the derivative of it. So we're in essence going to say that's u. So what's the derivative of e to the u? Just e to the u. Right? So we replace sine of x with u. Does that part make sense? Okay. So now y becomes the derivative of u times, in this case, e to the u, because that's the derivative of that. So we have cosine of x times e to the sine of x. And that's it. So we've taken that piece and we've made that the u. And then this became that part. So what do I want to make u? So we're going to make u 3x to the third minus 5x squared plus 2. So what's u prime? What's the derivative of u? And that's it, right? Because 2 goes away. And then I have u to the 8th. And if I do the derivative of that, what do I get? 8u to the 7th. Right? Do those two things make sense? Everybody can do those two parts? Now I got to put them together. So it's u prime times 8u to the 7th. So u prime is 9x squared minus 10x times 8, 3x to the 3rd minus 5x squared plus 2 to the 7th. Does that make a little more sense than what we did on Thursday? For those that at least your facial expressions made it look like you were totally lost. Okay. Look at one a little more complicated. I really like using these letters. I'm going to leave the letter in there this time because, so K is just a constant. We're not worrying about K. So what's U going to be? Three x K minus 4x. Find the derivative of that. What's the derivative of 3x to the K? Almost. You forgot the exponent on the x. So it'd be K minus 1. And what's the derivative of negative 4x? This negative 4. So then I have u to the 1/2 power, right? So I have square root of u, which is u to the 1/2. What's the derivative of that?
1/2 u to the negative 1/2.
Right. Which is 1/2 square root of u. I will tell you that you are going to see that a lot. The square root of something. Get into the habit of knowing it's just that without doing the steps. That's good. So one of the nice things about the way we're doing a lot of these things is once you know the process to it, you don't necessarily always have to keep redoing the process to get there. If you know the derivative of the square root of u is 1/2 square root of u, you can just go there without having to do the extra couple steps in the middle of it. That becomes almost like a rule, like sine goes to cosine, for example. So you don't necessarily have to go through all the steps for it. You just know it. And square root of something comes up enough times that happens. All right, so now I plug in the y prime is u prime times 1/2 square root of u. So u prime is 3k x k minus 1 minus 4 over 2, 3x k minus 4x. All right, I'm not seeing the totally and utter lost faces sitting in front of me. Hold on. All right. Everybody remember that rule? That actually comes from, remember if we go back a step. Because we can take that and move it down in front, correct? Remember that rule from LNs and logs and everything else? Vaguely, maybe. One of the rules for logarithms is that you can take any exponent down from the inside and bring it down in front. That's actually one of the ways that we use logarithms to solve things. So this would have become x ln of e equals x. And the natural log of e is 1. So x equals x, which works. Okay. Did you want that back? Here. There you go. Before I remove it all. No problem. Okay. All right. So if I was to take this side and raise it to the r power, what would I have to do to the other side? I would have to do the same. So I'd have to do this side to the r power. So this ends up being ln e how do I write this? Hold on a second. Oh, actually, hold on a second. Never mind. All right, let's do this a little differently. XL. Not that. We know those two. That was the other piece. If I raise both sides to the e, e and ln cancels each other out. So this side is just x to the r. And this side becomes e to the rn L of x. Which is just that. Correct? Does that make sense? Yes, no? Go ahead.
For the, you scroll up. How does the x on the right side of the equation turn into e to the RLN?
It doesn't. This does not go with that.
Oh, okay.
That's a different rule. It was a rule. It's just, it was a step we used to get to this. So 1, 2, 3.
Oh, so that's entirely.
Huh?
So the one that,
It was a separate rule. Yeah,
okay.
they didn't go together. All right. Does that step make sense? The 3 steps we just did.
Number one is E.
E to the ln of x r equals e to the r ln of x. So this rule, this is the basic. Nope, that's not what I wanted. That's what I wanted. That's the basic rule, and I did either. I raised it both sides to e, so that the e and the ln cancels each other out, because that's how we get rid of those. And I'm left with that. Now, there's a reason we're doing all this. So if I had this, those in essence are the exact same thing, right? The difference is that's the number, and that's going to be a number in this case. So the variable's in a different spot, but those two are basically the exact same rule. Correct? Awesome. As long as everybody agrees with that. You still need it. Okay. See where I'm going with this in a second. So, what is the derivative of b to the x? I don't know yet. So, these two are the exact same thing. So let's do the derivative of e to the ln b of x. Because they would be equal to each other. What can I do with this x up here? Using the ln rules we've just talked about. That would come down in front, correct? Okay. So I would have e x ln of b. Yes? No. I'm going to get you guys little buzzers. All right. Is that a variable or a constant? Because we're not differentiating on based on b. We're differentiating based on x. So any other letter is, in all intents and purposes, a constant. So the ln of b is a constant in this respect. Okay. So now let's do our chain rule, because I have e raised to something else. So u is going to be x ln of b. So what's u prime? What's the derivative of x ln of b? Yes. Just ln of b. What's the derivative of 3x? 3. Derivative of 5x? 5. If ln of b is a constant, it's no different than 3 and 5. So in this case, that's just ln of b. And we've already determined that the derivative of e to the u is e to the u, correct? We've done that a few times already. So the derivative of this is u prime times e to the u, right? So it is ln of b times e x ln of b.
That also be this ln b to the power of dx. Following what you were showing before. Previous slide where x
Goes up. Yeah. So this is going to be ln of b e ln of b to the x.
Oh, I see it.
Now, what was that at the beginning? That right there.
You multiply.
Hold on a second. You're going to make your life more complicated. Just give me 1
I
second.
was just curious.
Yeah, you're going to make your life more complicated. This and the b to the x are the same, right? That, so
That little box you got highlighted.
those are the same thing, correct? Because that's what I started with at the very beginning. That blue box right there is the same thing at the beginning, right? So this is really ln of b times b to the x. Because those two are equal to each other. All right, long-winded way to say this. The derivative of b to the x is ln of b to the x. So the derivative of 2 to the x is ln of 2 to the x. Because ln of b is just 1, so that works. Any other number that basis, it's got to be multiplied by the ln of that number. And the only reason I couldn't show this before is because you needed the chain rule to do it. Do you remember when I said, why did we, when I remember the whole conversation about, I'm showing you the rule for e to the x, but I'm not going to tell you why it works? This is why. I needed the chain rule to be able to actually show you why it works.
The confusion is whatever you, is this under for b to the x, is this under the clause that b to the x is equal to e to the 6?
Well, that's true. So b to the x is always, so b to the x equals that.
I just don't get where natural log comes from b.
In the, wait, here?
Yeah, kind of everywhere.
Okay. So I guess the premise
Like,
is,
that under that premise, that clause. Only- Like if we're considering b to the x equal.
you have to assume that this is true, but this is true. This is mathematically true. this and this are the same thing. Because E and ln would cancel out. So this right here is really saying b to the x equals b to the x. Because the E and the ln will cancel each other out. So this right here is mathematically equal to each other. Because that's mathematically equal to each other, I can do the derivative of either side. And it will give me the exact same thing. Okay. So since I don't know the derivative of b to the x, but I do know the derivative of something with e, we're doing the derivative of the e side. So the first step that I need to take is I have to pull that x down. So it's not in that exponent anymore, which I can do because of the log rules. Now I have e to the ln of, or e to the b, x ln of b. Correct? Yes? Okay. So now I'm going to use the chain rule to take the derivative of this. So the derivative of the top piece up here ends up being just ln of b, because the x goes away based on the power rule. So in essence, I worked through that whole process to find the derivative of that. And then I replaced that back with what the original statement was, which is that's b to the x. So instead of finding the derivative of the side I couldn't do, I found the derivative of the side I could. Or in essence, I rewrote it into a way that it could. The nice thing is you never have to do that again. Now it becomes a rule. That's the rule. And it always works. It even works with e to the x. E to the x is just easier to remember that it is e to the x and not having to go through that step, but it works. So A we already did, but g prime of x is just ln of 2 to the x. Now, b I have to do an extra step. Why do I have to do an extra step for this one? Because it's x squared. Because of that x squared right there. So I'm going to make what? I'll make u x squared. So what's u prime? Two x. So the 5x squared becomes 2x times ln 5 times 5x squared. Find me the derivative of that. What's U?
25 minus x squared.
What's U prime? What's the derivative of the square root of U?
1/2 square root of u.
So Y prime is negative 2x over 2 square root of 25 minus x squared. Or negative x over 25 minus x squared. So that's y equals 25 minus x squared. What does it look like? It's a half circle, right? Semicircle. And if I did the negative version of it, would have been the other semicircle, right? Would have made the whole circle. This right here, that's the derivative of it. So that's the derivative we just found. Does it look like it works? This is going to infinity, right? That's going to negative. It's going down. So it's going negative infinity. That's at 0. So it looks like it works. So it's good. The question is how did you do the derivative of that? If I had the whole thing. So circle is actually kind of easy because I can solve it for the plus version of it. and the minus version of it, right? To make the circle. So I could have the two derivatives for it. But can I take every equation that I ever have, any kind of anything, and solve it for y? Can every equation be solved for y?
of those.
That's simple, right? I can solve this for y. Square both sides, y equals plus or minus the square root of 25 minus x squared. Simple enough, right? What about this one? How did I solve that? Can you?
Or what?
Huh?
Solving.
Solving for y. Could you get the y by itself? Probably not. So, but is that an equation? Is it a function? What's the difference? What's the difference between a function and an equation?
Function has one output for input.
So is my original problem at the top, the x squared plus y squared equals 25 a function? No. And y equals plus or minus the square root of 25 minus x squared. It's not a function. If I erased the plus or minus, that's a function. But by in essence having that plus or minus, it makes it not a function. I have two answers on it. Same thing with the bottom one. These are equations, but not functions. Even though it's an equation, I still should be able to do a derivative of it. So I need to be able to take the derivative of any equation. So let's go back and look at the circle. We'll do that. All right. So if I want to do the derivative of this, I have to look at taking the derivative of both things. So we want the dy dx of this. So what is the derivative of x squared? That's 2x. What's the derivative of y squared? What's y typically? Y is typically the answer, right? So y is a function. Y has got other things in it. So what you have to do is you're actually going to multiply it by y prime. Whenever you take the derivative of y, you're going to multiply it by y prime. That's in essence the derivative of whatever y is. What's the derivative of 25? Sure. Actually, I'm gonna rewrite this. I'm gonna write this as separate steps. Does each of those steps make sense? Or do you understand each of those steps? So whenever you do the derivative of x, you just leave it. If you're doing the derivative of y, you have to put y prime next to it.
Why is it?
Because y is typically an equation. If you're looking at a graph, you're solving for y by plugging something in for x. Y is something you're solving for. You're not typically given it. Since something you're typically solving for, it is its own function in essence. So that's where that chain rule comes in play. In essence, that's the chain rule. It's 2y, that's the derivative of that, times whatever the derivative of y was. That's just like we were doing way back at the very beginning with the u. That's your x. That's your y. So it's y prime times the derivative of that. Okay? Does that make sense? Think about y as a function that you have to actually take the derivative of whatever that is. Because it's not an x. Because remember, we're only doing the derivative in terms of x. So if it's a y, that's another function. That's why you have to have y prime. We're not done yet, though. The last step you have to do with this, you have to solve for y prime. You want to get the y prime by itself. So how do I solve this for y prime? Now think back to your algebra. That's the first step.
Subtract the 2x.
Yep. So I have 2y y prime equals negative 2x.
And then divide both sides by 2y.
So y prime equals x over y. Oh, I didn't forget the negative here. Right? I did forget the negative.
For the derivative is
No, the derivative is negative x over y.
no, but of the circle overall. So you're to plug y
So,
prime into that.
the derivative of that is that. So on that circle, I could pick any point, and I'd plug it into that, and it would find me my derivative. So let's say, let's find a point on here that works. Negative 4, 3 is on this circle, right? That's right there. So if I have point, my xy is negative 4, 3. So my y prime at that point would be 4/3, right? Okay, let's see. We did this before, correct? And we said the derivative of that would be that right there, correct? That's when we did it the original way. Let's plug the -4 into that and see what we get. So if x is -4, let's see what we get. So I get 4 over 25 minus 16, 4 over square root of 9, 4/6. So and remember, the derivative is trying to tell me my slope. So my slope at that point for both ways is 4/3. The question is which one's easier to work to? This one's probably easier to do. And this one gives me the ability to do any point. It doesn't necessarily have to be on that top of the part of the circle, or I'd have to do the other bottom of the circle. I could do any point. All right, let's look at that other horrible equation I did. That's what that equation looks like. X to the third plus y to the third equals 6xy. There's that wonderful little loopy thing. It has a name. That's what it's called. So let's find the derivative of it. What's the derivative of x to the third?
X squared.
3x squared.
That's 6xy.
Yes. What's the derivative of y to the third? Yeah. What's the derivative of 6xy? What's that on what 6xy is what? It's a product, right? You're multiplying. They're not constants. Y is not a constant. If y it was any other letter, y it'd be a constant. Y is not a constant. I have to do the product rule for this. So I have 6x in essence times y. I have to look at this as a product rule. So what's the derivative of 6x? And the derivative of y is just y prime. So I have 6y prime plus, oh, that's 6y prime. 6y plus 6xy prime. That will be the one that will always screw you up because it's really easy to think of, oh, that's not a product. You have to remember it's a product. If I did 6x divided by y, nobody in here would have thought, oh, that's not a quotient. You'd have automatically assumed it's division. But when they're next to each other like that, you kind of forget that it's a product. All right. I need to solve for y prime. So how can I solve for y prime? This is where that algebra comes back into play. Like, I know it sounds like, oh my God, this is a calculus problem and everything else like that. We've done the calculus. Now it's manipulation. This is just an algebra thing. So think back to your equations. When I was solving for a variable, what was the goal? What was the first thing I would have to try to do? Get all the variables on what? One side. I want to get all the variables, the ones I'm solving for, on one side and everything else on the other side, correct? So I want to get my y primes to one side and anything else that doesn't have a y prime to the other side. So let's move this over here. And we'll move the 3x squared over to the other side. So I have 3y squared y prime minus 6xy prime equals 6y minus 3x squared. All right, what's next?
On the left side of the equation, you can factor out y prime.
Yeah. The reason we get them all to one side is because now everything over there has a y prime in it. Pull it out. What operation is that now? Y prime what? The parenthesis. Times. How do you get rid of multiplication? Divide. So y prime equals 6y minus 3x squared, 3y squared minus 6x. I can technically divide everything by 3's. You do not have to, but you can. And that's my derivative. All right, find me the derivative of that. I have a product. So negative 19x squared, y squared. So I have to do this as a product rule. So now we can clean up this side a little bit. And I got to get my y prime by itself. So we'll move one side over. And now divide both sides. And I get negative y over x. Does the process make sense? Everybody good writing it down?
Nice.
That's it. On Thursday, actually going forward, I'm going to move the class over to my other classroom. We lost a couple people, so everybody will fit. I'll put a sign on the door and I'll come get people on Thursday if you're totally lost. We'll be over at E206. It's literally right around the corner. Huh? So that's my actual classroom that I'm in all day. And I like the setup of it better.
You're good to switch off.
Huh? Okay. I don't think I see anybody else writing. Saves me having to walk over here and all my other stuff is there. And when I do the test, I have all the plugs and everything else for computers and everything else right there. So it works out nice. So now this one, we've got 4 different pieces we're doing the derivatives of. So what's the derivative of negative 5y to the 7th?
Negative 37, y to the 6 times.
35.
Oh, I say 36.
Yeah. So you said 37, actually. It's okay. I knew what you totally knew what you meant. You saw the 7 and knew when 7 in your head. Yeah. All right. What about this one? This is a what? A product. So I got to do this as a product. So negative 8x to the 9th goes to negative 72x to the 8th. And y goes to y prime. So I have negative 35y to the 6th minus 72x to the 8th y minus 8x to the 9th y prime plus 2x equals 0. I can't write. There should be. There should have been. Good catch. So now we leave the y primes. Everything else goes over the other side. Factor out the y prime. And divide. Most of these do not come out nice. Most of these, the answer is kind of messy, especially if there's multiple y primes, because you're going to have that division stuff in there. Two, one. So what's the key piece of implicit differentiation, which is what this is called, that I screwed up on this topic? Anytime you have the y in there, you have to have a what? A y prime. Anytime you take the derivative of y, you have y prime. All right, one more. So sometimes when you're doing these, it's actually easier to do this them as two separate steps. All right, let's look at this one first. What do I need to do for this one?
Find year.
Because I have to do the chain rule for this one. So what's u going to be in this situation?
7x minus 5y.
So u prime is? What's the derivative of 7x? Derivative of 7x is just 7. What's the derivative of 5y?
5y.
Almost. Just 5 prime. Just, oh, yeah, it's actually, never mind. Yes, you said 5y prime. Yes, that's right. I doubled the y when you said that. Because that's what I was expecting to hear. Yeah, because the derivative of 5y is just 5. And then the y prime. All right, what's the derivative of square root of u? Or u to the 1/2.
1/2 square root u.
Right. So the first side becomes 7 minus 5y prime over 2 square root of 7x minus 5y. So what do I got to do on this side? This is the product, right? So 2x goes to 2, y goes to y prime. So I've got 2y plus 2x y prime. really want to see something. I think. All right. We now have to solve this for y prime. I see people still writing, so I'm giving them a chance. Okay. All right. What do you want to do first?
Multiply both sides of the equation by, how many of them?
Yeah, let's get rid of the fraction. At least let's try it. Start there. So I have 7 minus 5y prime equals 2 square root of 7x minus 5 times 2y plus 2xy prime. All right, next step.
That would be two.
Just because I got to get that y prime by itself, so I just got to get it out of there. Okay, next step.
The terms with y prime is one side of the equation.
Yep. Now factor out the y prime. And divide. All right. Other than the algebra, does anybody have a problem doing what's on this screen right here? All right. That's the calculus. Right there, that's all the calculus. Everything else we did on this problem is all out. If you understand this, you got the calculus. The algebra is going to trip you up. I know it's annoying. It's tough. There's lots of little things you can mess up and stuff you can screw up. But if you can understand this right here, that's the calculus part, and you understand how to do its implicit differentiation, which actually is not the easiest thing in the world to do. So we've gone from being able to take the derivatives of functions to now being able to take the derivatives of any equation, not just functions.
Did we get to the final one for you?
Yeah. That big mess down the bottom. If you had gone the other direction, your signs might be different.
Yeah, my son.
Yeah, your sign should be, if you did it the other way, every one of your signs should be opposite of mine.
Other
Which,
than what's in the square root.
yeah, other than what's in the script.
And then would that still be correct?
Yes, absolutely. Yeah. I don't know why the, did I close it? Oh, I closed it. If it gives me the same problem. Doesn't. They actually did the answer to this problem. This is a different problem, but same process. And they have negative exponents on the square root. I don't know why. I don't know why they chose to do it that way.
I was just kind of like set for all the problems.
Yeah, I've noticed that. So I actually just got an email today asking how it's going. So actually, that's a good place to end. Are there any, so other than those few things that I noticed that have you noticed anything on your end? Because most of you have used Alex for pre-calc, right? Have you noticed anything drastically different that you don't like with the way they're doing calculus? Or, yes, I have noticed that. And
You get a question you don't